Hi, welcome to ACE Teachers Online, a series of online tutorials for students. My name is Sai, and today we'll be looking at the concept of the ideal gas law. So today we're going to be learning about the ideal gas law. The ideal gas law is actually a combination of three previous laws that were developed by three different scientists years ago. The first one was developed in 1662 by an Irish chemist known as Robert Boyle. Based on experiments that he conducted, he determined that the volume of a gas was inversely proportionate to its pressure. So in essence, if you decrease the volume of a gas, you'd be increasing its pressure, and vice versa. Then in 1787, Jacques Charles came up with a notion based on his experiments that the pressure of a gas was directly proportional to its temperature. So if you increase the temperature of the gas, you'd be therefore increasing its pressure. And lastly, in 1811, Avogadro, the Italian chemist, came up with a notion that if equal volumes of gas at the same temperature and same pressure contains equal number of moles. So in essence, he stated that the volume of a gas is proportional to the number of moles of that gas. Now, if we combine all three of these laws together, we get our equation, which is the ideal gas law, PV equals nRT, where R is your universal gas constant, the value of which would depend on the units that you specify for your pressure, volume, and temperature. Alright, so what does it mean for something to be an ideal gas? There are no gases in the realistic universe that actually are ideal. And to be ideal, it has to satisfy these three assumptions. Firstly, that there are a large number of molecules within the gas that are always in random motion, and they always obey Newton's laws of motions. Secondly, the volume of the molecules of the gas is negligible compared to the total volume occupied by the gas. And thirdly, there are no forces acting between the molecules except during the negligible time of elastic collisions between the molecules. So these are three assumptions of an ideal gas. As I said before, there are no gases that are actually ideal. However, real gases tend to obey these rules at very high temperatures and very low pressures. So as the temperature increases and the pressure decreases, they approach these ideal conditions. As such, we can use the ideal gas law as a means of doing calculations as long as the question says we can assume that the gas is ideal. So now we're going to look at a question that requires us to apply the ideal gas law. So just a refresher, the ideal gas law is PV equals nRT. Alright, so now if we look at our question, it says that we've got 10 grams of magnesium dissolved in excess hydrochloric acid. And then if we write the equation for what happens during this reaction, we know that an aqueous salt and a gas is produced. So the chemical equation would be magnesium plus 2HCl gives you magnesium chloride, which is our aqueous salt, and hydrogen gas. Now, the question asks us to determine the pressure of hydrogen gas if it is known that the reaction occurs in a 1 liter reaction chamber and the temperature of the chamber is 50 degrees Celsius. So if we look at our ideal gas law, we want to calculate the pressure, we know the volume, we know the constant, and we know the temperature. So the only thing we're missing from this calculation is a number of moles of hydrogen gas. So how do you calculate the number of moles of hydrogen gas? This goes back to basic molar calculations. First step that you'd have to do is always write your equation, which we've got here. Remember, for every question, always write your chemical equation as your very first line. The next step would be to determine the number of moles of the known substance. In this case, our known substance is magnesium. So the number of moles of magnesium would be equal to the mass of magnesium divided by the molar mass of magnesium. So in this case, that's 10.0 grams on 24.31, which gives us 0.411353 moles of magnesium. So now we look at the ratio between magnesium and hydrogen gas. So if we look at the ratio, we know that the ratio, or the molar ratio here, is 1 to 1. So therefore, we know that the number of moles of hydrogen gas is also equal to this, 0.411353. Now that we know the number of moles of hydrogen gas, it's all just a matter of plugging it into our formula to determine the pressure. So let's look at case 1 here. Volume is 1 liter and the temperature is 50 degrees Celsius. So, first thing that we do, write out a formula again, PV equals nRT, and rearrange this formula so that the thing that we are looking for is isolated on the left-hand side. So if we do that, we get P equals nRT on V. Now, if we sub in all our numbers, the one thing that you have to realize is that the temperature always has to be in Kelvin. So in this case, 50 degrees Celsius is equal to 323 degrees Kelvin. So we have to make that conversion, and the conversion is just adding 273 degrees. Okay, the next thing that we have to know is the value of R varies depending on what units we want our pressure to be in. The two most common are either kilopascals or atmospheres. So in this case, the question asks us for kilopascals, so the value for R is actually 8.314. If it instead asked us for atmospheres, the value for R would be 0.08206. You can always just determine your answer in kilopascals first, then convert to atmospheres later, because the conversion is 1 atmosphere equals 101.3 kilopascals. Now, if we plug in our numbers into this formula, we get that the pressure of hydrogen gas equals the number of moles, which is 0.411353, multiplied by 8.314, multiplied by the temperature, which is 323 degrees, divided by the volume, which is 1. Plugging those numbers into a calculator, we get a pressure of roughly 1,104 kilopascals. Okay, so now that we've done that, obviously in this question you would always round that down to the correct number of significant figures. So in this case, if they only gave you 1 liter, this would ideally be given to 2 significant figures. So 1.1 times 10 to the 3 kilopascals. The second case asks us to consider the situation 15 minutes later, where the temperature drops down to 20 degrees Celsius. So there are a variety of different ways that we can do this question. We can again just use this formula, the rearranged version of this formula, and plug in all our numbers with the new temperature. Or we can use the adaptation of Charles' law, and that was P1 on T1 equals P2 on T2. I always prefer using this method. The reason why is because that means that you do not use a number which you've already calculated. So in essence, if I got this question wrong, I could still get the second part of the question right because I'm not using my wrong answer in the second part of the calculation. However, just to show you how this equation works, I'm going to do it the second way. So in this case, I'd rearrange this for P2, which is what I'm trying to find, and I get P1 multiplied by T2 on T1. Again, if I sub in my numbers, I get 1104 multiplied by my temperature, which I have to add 273 degrees to. So I get 293 Kelvin multiplied by 293 on 323. That gives me 1002 kilopascals. Yeah, again, if I wanted to round it to 2 significant figures, 1.0 times 10 to the 3 kilopascals. So this is a basic concept of doing any ideal gas calculation. First thing first is, if the question requires you to determine the number of moles, just go about your normal basic molar concept calculation to find the number of moles that are required. Then rearrange your ideal gas law formula to give you the subject of the thing that you actually want to find. In this case, for example, it was pressure, so we rearranged to make pressure the subject. Now, the key things to always remember are, remember what the value of your constant should be, determined by what the units of your pressure should be. And also remember to convert your temperature into degrees Kelvin rather than degrees Celsius. So in summary, today we've looked at the universal gas law. We looked a little bit about the history of the laws and the laws that preceded it. We also looked at the universal gas law and some of the assumptions that are made to assume that a gas is ideal and satisfies this law. Then we looked at a calculation based on applying this ideal gas law to a given situation. Main thing I want you to take away is how to approach this calculation and the steps in doing it. Remember that temperature is always in degrees Kelvin, and that the universal gas constant R has a different value depending on what the units of the pressure are. So hopefully this video was helpful, and the main thing I want you to take away is that chemistry is not that hard.
Thanks for watching this video. For more information, look at our website down below and keep tuned for more ACE Teachers Online.